We're going to be starting Unit 6 today and looking at how you find area. Now, we've done it before where we found area under a curve, but today we're going to look at how do you find it between two curves. So if we have this red function here, f of x, and we want to find this brown area between f and this blue function, g of x, how do we do that? Well, if we were to just find the area under f of x, it would give us all this area between that and the x-axis. If we would just find the area of g, it would give us this blue area between g of x and the x-axis. Well, the brown stuff is the difference between those. So if we were to take the red area and subtract off all this blue area, we're left with what's in brown. So how we find this then is to take and subtract the two functions. And when you subtract it, you always want your top function first and your bottom function second. So you're doing top minus bottom, and the difference would be what you end up with. We can do that even if your function goes below the x-axis. Because if we run into this situation, f of x would give a area under would give us that. If you minus then g of x, which is this area here, that's negative. It's like minusing a negative, which in turn still gives you the area you want. So you're really adding area, and then when you minus a negative. So it'll work even for functions that go below the x-axis. As long as you take top minus bottom, it should work out. All right, so let's try one out here. The first example says find the area of the region bounded. Bounded means like enclosed by that. The different equations are going to be the outside of the shaded part of y equals e to the x. It's this red or pink line here. And it's bounded below by the line y equals x. And bounded on its sides by these two functions, x equals 0 and x equals 1. Well, you've graphed x equals lines before. Those are vertical lines. So x equals 0 would be this line. X equals 1 would be this line. So it's basically just chopping off the graphs at those 2 points. All right, so to do this, we know finding area means we need to set up an integral. So this is going to be the integral from x equals 0 to x equals 1. And then we want to subtract these two functions since our area is in between. So we want the top one, which in this case is e to the x, minus the bottom one, which is just x. And then we're integrating with respect to x. So now if we solve this out, it should give us the area there in brown. Okay, so to solve this, you need to do antiderivative. All right, so antiderivative of e to the x is e to the x. And antiderivative of x would be, we gotta go up a power, x squared. And the reciprocal would be 1/2. And then we want to evaluate this at 1, 0, and 1 and 0. So now if we go through and plug in those numbers, we should get the answer. If we plug in 1 and 0 here, it's going to be e to the first power minus e to the 0 power. And then minus here, what we get when we plug in the other ones. So we got, I'm going to leave the half out here. So if we plug in 1, it's going to be 1 squared minus 0 squared. Okay, on this first one, when we evaluate it, e to the first power is just going to be e minus e to the 0 is equal to 1 minus all this stuff. 1 squared is 1 minus 0 is 0. 0 squared is 0, so that whole thing just is going to simplify to 1. 1 times a half is going to be 1/2. And so our total answer here, or our exact answer, looks like it's e. Negative 1 minus another half is minus 3/2. So that would be the area in whatever units squared there. So that would be our area. So it's just, this is where the integrals actually can help you find stuff. All right, let's try another one here. The next one says find the area of the region enclosed by the parabolas y equals x squared and y equals 2x minus x squared. Now, on a problem like this, it might be helpful to kind of see what this looks like. So let's graph out, kind of see what we're dealing with here. So let's graph both of those, x squared, and we also are going to be graphing 2x minus x squared. If we graph, we see that you get these two parabolas here, and I'm gonna go in a little bit closer so we can see that a little bit better. And you can see there is this overlapped area in here that we want to find. Okay, so what we got to figure out now is where, kind of looks like this. We want to find what's this area right here, because that's the area enclosed by these two graphs. Okay, so we want to know where's this point and where is this point going to be. Now, sometimes you might get lucky and you can tell from the graph, and I think on this one you can tell, it looks like at 0 and 1 that those are going to be crossing at, so 0 and 1. Now, that works sometimes when your graph is nice, but what happens if you want to find where these intersect and you can't tell from the graph? Well, if you want to know where two lines intersect, you can always set them equal to each other. So if we were to set both of these two equations equal to each other and solve, it should give us these same 2 points of 0 and 1. Let's do it just to show you here. So to solve this, you could add x squared to both sides. So that cancels out. So now you got 2x squared equals 2x. Let's get let's actually move everything to the same side here. Let's minus another 2x. Let's get this equal to 0. And now we can do some factoring if we factor out 2x. Now if we set both factors equal to 0, we should get the two places these are going to intersect. Here if we divide by 2, it's 0. If here we add 1, we get 1. Same two things we got here of 0 and 1. So that's how you can do it algebraically if the graph doesn't provide you with enough information. Okay, well that's great. So now we should be able to set up our integral. We know it's going to be from 0 to 1. We also got to figure out now which one's on top, which one's on bottom. So here's our graph of x squared. And this one going down here, it was the one 2x minus x squared. So it looks like the one that was on top is the 2x minus x squared on top, minus the one on bottom, which is x squared. So if we find this and integrate it, it should give us our answer here. So we'll start by finding antiderivatives. Or another thing we could do is look at simplifying. I think we can actually simplify here a little bit before we find antiderivative. We got some like terms here. So we could write this as 2x. And we got negative x squared minus another x squared. That would be minus 2x squared. Okay, so finding our antiderivatives, the first one would be x squared. We want to evaluate that at 1 and 0. Minus our second one here, if we go up power, it would be 3. Reciprocal is 1/3, but we got another 2 there, so it looks like there's going to be 2/3 evaluated at 1 and 0. So now plug these in and see what you get. This would be 1 squared minus 0 squared for the first one, minus 2/3 times, if we plug 1 in here, it's 1 cubed minus 0 cubed. Going farther here, 1 squared is 1, minus 0 squared is 0, so that's just going to be 1, minus 2/3. That also evaluates to 1, so we got 1 minus 2/3, which is 1/3. Unit squared would be the area. how would we find the area between these curves? So if we want to find what's this total area here plus this area here plus this area here, how would we do that on this one? Well, this one's a little bit harder because as you can see they kind of overlap here. So right here on this first one, f of x is our top one and g of x is our bottom function. But then in the middle here, they flip-flop. Now g of x is on top and f of x is on bottom. And then it goes back to f of x being on top and g of x being on bottom again. So what you would have to do on one of these is kind of split it up. We would need to know some other information here. We need to know, where's this point at? Let's call it C. Where's this point at? Let's call it D. And how you would find those 2 points C and D is by setting the functions equal to each other and solving. So if you set f of x equal to g of x and solve, then you can find C and D. Because wherever they're intersecting, whenever you set two equations equal to each other, you'll find where they intersect. Okay, once you do that, then you should be able to set up some integrals and solve this one. So the first one you would set up from A to C, and then here with the first one, f of x is on top, g of x is on bottom, so we'd subtract it like this. Okay, plus, okay, now the second one goes from C to D, and here now g of x would be the one on top, minus f of x on bottom, and then plus one more integral from D to B, and again, f of x is back on top, g of x is on bottom. And then if we solve this out, this first one would give us the area of S1, the second one would give us the area of S2, the third one would give us the area of S3, and then we would add those up and we'd get the total area. So that's how you would handle any time that you get one function and then it kind of switches back to the other. Another way we could write that would be saying it's the absolute value of one function minus the other function, because absolute value would keep everything positive while you're doing it. Now, does it matter so much here when you do absolute value? No. Whatever this solves out to be would give you the same thing as if you had g of x minus f of x. So if you're talking absolute value, you just got to make sure that everything stays positive. So let's try one of these. Well, how would we solve number 5 here? It says find the area of the region bounded by the curves sine x and cosine x from 0 to pi over 2. Well, you can see this first area in pink here has a different function has cosine function on top, sine on bottom. Once they hit this point in the middle, though, now it switches. Okay, so we would want to set up two integrals to solve this one. So the first one would be from 0 to, looks like pi over 4 is where they're splitting up here. And it would be cosine x minus sine x plus, now our second one goes from pi over 4 to pi over 2. And they flip-flop now. So absolute value, you got to make sure you're doing the top minus bottom. So this would be now sine x minus cosine x, the opposite of what we had before. And if we solve that out, that should give us the answer. So now you'd want to find antiderivatives and keep going from there. Antiderivative cosine would be sine of x, evaluated from pi over 4 to 0. Minus antiderivative of sine is negative cosine of x from, again, pi over 4 to 0, plus antiderivative of sine x is negative cosine. This one is from pi over 4 to pi over 2. Minus antiderivative of cosine is sine. Pi over 2 to pi over 4. Okay, so now you'd want to plug these in and do it. Now, make sure your calculator's in radians when you're doing these, otherwise they're not going to come out right. So this first one, if we do sine of pi over 4, we get this. Now, this is one of those either you need to know from the unit circle, or you kind of have to have that decimal number memorized there. 0.707, that's the same as square root of 2 over 2. So if you took square root of 2 over 2, it's the same value. So this first one here is square root of 2 over 2 minus, if we plug in sine 0, we get 0. Okay, next we got minus and negative here, so that's going to turn into a plus. Now we want to do the same thing. What do we get when we plug in cosine for these? Cosine pi over 4 is, looks like square root of 2 over 2 again. And then cosine 0 is equal to 1. This next one, we got plus a negative, so I'm just going to turn that into minus. And then we got cosine pi over 2, so let's plug that in. Cosine pi over 2, that's 0. So we got 0 minus, and we've already done pi over 4, that gives us square root of 2 over 2 minus. Now we do sine pi over 2. We get 1 minus square root of 2 over 2 again. Okay, so if we simplify that, that should give us our answer here. Well, that's square root of 2 over 2 plus square root of 2 over 2 minus 1. Now this one, this is going to be minus a negative here, which is going to turn into plus square root of 2 over 2. And then in this last one, be very careful, it's minus again. So it's almost like we got to distribute that negative sign to both, because we're minusing two things here. Minus 1 plus square root of 2 over 2. All right, simplifying that out now. It looks like we have a total of 1, 2, 3, 4 of these square root of 2 over 2's being added together. So we got 4 square root of 2 over 2's. And then we got minus 1 minus another 1 minus 2. Simplifying that a little bit further here, you get 2 square root of 2 minus 2. Looks like our answer. So that would be our area for this one. All right. How would we find this next area between these two curves with these functions? Well, now we're kind of stuck here. If we were to just do our top minus bottom thing we've been doing, we kind of run into trouble here. Because for one, the top's not always the same here. If we were to take right here, the top is that and the bottom is this straight across line. Or if I'm going over here, all of a sudden my top isn't, it's this straight line, and I hit the graph, and now even though there's another part over here, it gets really confusing, and the top minus bottom thing doesn't work so well anymore. So there's another way we can do this, and rather than doing top minus bottom, we can think about going from left to going left and right as well. So if you have two functions where top minus bottom doesn't work, you can also do the same thing by selecting your function on the right and minus the function on the left, as if you're going around the y-axis. So we got to switch our thinking now. We're not going around x-axis anymore, or using the x-axis as our point of reference. It's the y-axis. So our upper and lower limit is not coming from the x-axis anymore. It's actually coming from the y-axis. So we want to find where to integrate them from that location. Also, when we're doing this, notice our function's not x anymore, it's y. So you need to solve your equations and have y as your variable, not x anymore. Let's look at an example of where you'd use something like this, another example. So on numbers, example 6 here, it says find the area enclosed by the line y equals x minus 1 and the parabola y squared equals 2x plus 6. Okay, so here's what we were talking about before. If we did top minus bottom, top and bottom is actually the same function right here. That would get really confusing. But whereas over here, it might work a little bit. So top minus bottom is not going to work. However, if we did our right function minus left function, the whole time here, this is our equation on the right, and this blue equation is always to the left. So we can use right minus left to do this one. All right, so to do this, we want to set up an integral to find our area. Okay, so we got to figure out which function is on the right. Well, the one on the right is y equals x minus 1. But we can't use y equals x minus 1 and write that in our integral because we need y as our variable. So what we got to do is take this equation y equals x minus 1 and solve it. Instead of y equals, we want to solve for x equals, find the inverse. So to do that, add 1 to both sides and we get x equals y plus 1. Okay, so all we're doing here is adding 1 to both sides. Okay, so that's our one to the always to the right. So that one we're going to write in first in our integral here. Y plus 1. All right, minus now, okay, because that's our one, this is our function to the right. Now we want to find what is our function that's going to be to the left. Well, our function to the left here is y equals the square root of 2x plus 6. But again, that one's always to, that one's a y equals right now. We want an x equals. So we got to find the inverse of this. Okay, so back when in Algebra 2 when you were doing this is where it kind of is going to help you out. So we got to undo everything here. So first we got to get rid of that square root. We can do that by squaring both sides. So now we got y squared equals 2x plus 6. Okay, now we want to get that 6 out of there, minus 6. Now we got y squared minus 6 equals 2x. And then finally we want to divide by 2 here. If we do that, we end up with x equals 1/2 y squared, and 6 divided by 2 would be 3. So that would be our function to the left. Okay, and this one is going to be dy because everything is in terms of y. All right, now the last thing we need is our limits. What's our limits going to be? Well, that would be where these are intersecting on the y-axis. So we want to know where's this location, and we want to know where's this location. Now, you can see from the graph here what they are going to end up being. It looks like it would be at 4 and -2. Now, that graph provided that for you. What would you do though if if you didn't have a graph provided like this? Well, set the two equations equal to each other. Okay, so let's see what we would do. If we set y plus 1 equal to 1/2 y squared minus 3, how would you solve that? Well, this looks like it's going to be a quadratic, so you want to get everything to the same side. So minus y and minus 1 over to the other side here. Okay, so now it's equal to 0. We got 1/2 y squared minus y minus 4. That might be hard to factor or do quadratic formula with a fraction. let's multiply through by 2. So let's times both sides here by 2. So 0 times 2 is still 0. 2 times a half, this is just going to be y squared now, minus 2y, and then 2 times 4 would be 8. Can we factor this one? I think so. What multiplies to negative 8 and adds to negative 2? Looks like minus 4 and plus 2. Setting those both equal to 0 and solving, you're going to now get y equals 4 and y equals negative 2. Those are the same 2 points that we saw they were intersecting at. So 4 and negative 2. Now if we solve this out, we should get the answer. This one looks like we could maybe do a little simplifying right away here, so we don't have to find as many antiderivatives. This is like minus this and minus that. So another way we could write that would be y plus 1 minus half y squared plus 3, because it's minus a negative would be plus. And then it looks like we could combine two of these terms here. So we would have 1 and 3 would be 4. Okay, so now if we find antiderivative of all these and plug in our numbers, we should be able to find this area out. So first here we got antiderivative of 1/2 y squared, and we want to evaluate that at 4 and negative 2 plus. The middle one's pretty easy here. That's just 4y evaluated at 4 and negative 2. The last one, that's going to be y to the third power. Reciprocal would be 1/3, so this is going to end up being 1/6. And then, again, evaluating at 4 and negative 2. I'm going to leave these constants out while we do this here. So we got 4 squared minus negative 2 squared plus 4. It's going to be 4 minus negative 2 minus 1/6. And we got 4 to the third minus negative 2 to the third. Evaluating all this, we should be able to get to our answer. We got half of 16 minus negative 2 squared is going to end up being positive 4 plus 4 times. Here we got minus a negative. That's going to turn into plus. So 4 times 6. And the last one, 4 to the third is 64 minus negative 2 to the third would be negative 8. Going a little farther here now, we got half of 12, which is going to be 6, plus 24. And here we got 1/6. This is minus a negative, so this is going to turn into plus 72. And 72 divided by 6 would give us 12. So putting that all together, we got 30 minus 12, which would be 18 square units. All right, so whether you go top minus bottom or left minus right, or right minus left, just depends on the problem. I want you to try out some of these area problems now on your own.